Hello, welcome to electronics education. This is Vincent Chang. So we're going to continue our learning around the device physics of p-n junction. Device physics of p-n junction. So p-n junction in thermal equilibrium, part 2. So in this lecture, you're going to learn a very important concept of energy barrier. Energy barrier. The depletion layer will be formed for a p-n junction when it's in the thermal equilibrium condition. So on the left-hand side of the depletion layer of the p-n junction is shown the negative acceptor ion. But on the right-hand side of the depletion layer, the purple positive ion represent the donor ion. The electric field is built in, is established within the depletion layer. The left-hand side, the left boundary of the depletion layer is denoted negative XP. And the right boundary is denoted XN. Electric field versus potential. When the electric field is established within the depletion region, then there's another physical quantity called the potential. Field and the potential. Field and the potential. So now I'm standing on a second floor of the building, and it's influenced by the gravitational force, the gravitational field. So then the second floor, the potential is here, and then if I move up against the gravitational field, then I increase the potential energy will be increased, right? The potential or potential energy will be increased. So there's always association, relationship between field and the potential. So I was talking about the gravitational field and the gravitational potential, or gravitational potential energy, we learn from the physics. So same thing with the electric field and the electric potential. So what's the relationship between the electric field and the electric potential? This is the relationship. So electric field is the gradient of the potential. It's the differentiate of the potential. dV, dx. dV, dx. But why there's a negative sign? As I just mentioned, when you against the gravitational field, this is the downward. The gravitational field is downward, right? This is downward. The gravitational is downward. If you against, then you increased. That means the direction of potential increased is in the opposite direction of the field, right? That's the physical meaning of the negative sign. If you can understand this, then it will be very easy for you to draw this diagram. Now V of X means the electrostatic potential distribution along the dial, along the p-n junction. Electrostatic potential distribution. So on the blue region, no field. So no field means what? Means electric field is 0, right? Then electric field, look at the green equation. The electric field is 0 means what? Means potential is constant, right? So what constant? What constant? Could be any. It could be any constant. Any constant plug in, C1, C2, C3, plug into this differential, then you can get the same field. All right? So field is unique. Field is one and the only. But potential could be any. All right? So if potential could be any, for simplicity, for the sake of simplicity, let's just put a 0. Because the absolute potential means nothing. So what matters is what? It's the potential difference. It's the relative potential. It's the potential difference. Let me repeat that. So absolute potential doesn't mean anything. But what matters is the potential difference, right? So, because we can accept any potential, let's just put the zero. And then what? Then if you step into the depletion layer, then you have to follow a rule. What rule? When you against the electric field, then potential will what? Will increase. When you against the field, the potential will increase. And the rate of the increase depend on what? Depend on how strong the electric field is, right? Do you understand? dV dx means slope, right? So electric field, if the high electric field means higher slope. So degree of gradient depends on how strong the electric field. And then when you step outside the depletion layer, then you reach another constant. So this is the electrostatic potential distribution for a p-n junction. Then you see a high potential area on the right-hand side, a low potential area on the left-hand side. So you see a difference. So this type of difference is built-in. It's called built-in potential. This is called the built-in potential. The built-in potential of a junction. So it's very important to understand this diagram. The relationship between the electric field, electrostatic potential distribution, and potential difference, the built-in potential across the depletion layer of a p-n junction. So now I'm going to teach you another concept, very important concept. It's called concept of energy barrier. So we're going to take this concept when we move forward to a three-terminal device, so-called bipolar junction transistor, to understand the nutshell, the key concept of the transistor operation. And we start from here. So very important concept, the concept of energy barrier. Because V is the potential, right? The dimension of the potential is volt. That's volt. But what about if you times elementary charge? If you times the V with multiply V by elementary electronic charge Q. So 1.6 times 10 to the negative 19th power coulomb. Right? If you times the elementary electronic charge, the unit charge, then what? Then what? The shape, because you times the constant, so the shape won't be changed, but the meaning has been changed. From potential, the volt times the unit charge goes to what? Have you ever heard a term called electron volt? So electron volt is the dimension of what? It's the dimension of energy, right? Electron volt is the physical quantity to describe the energy, all right? So if you time the Q, this is the point. This is the concept. The form, the shape, the diagram won't be changed. The same. And then, but the meaning, the physical meaning has been changed from potential to what? To potential energy. So who owns the positive Q? Who carries the positive Q? The whole charge. So this diagram is the potential energy diagram specifically for hole. If you times the negative Q, then it flipped upside down, right? 180 degrees. If you times negative Q. So who carries the negative Q? Electron. So this is the potential energy diagram for electron. Again, this is the potential energy diagram for hole. This is the potential energy diagram for electron. In other words, from hole's perspective, if you live on the left-hand side, if you reside on the left-hand side, then you live in the low potential energy area, right? If someone boosts you up, give you some of the energy drink, then you can move up to the mountain, right? To the high potential energy side on the right-hand side. But from the electron's perspective, that's different. If you live on the right-hand side, then it means electron. From electron's perspective, from electron's point of view, this is the electron's valley. And then on the left-hand side is the electron's mountain. Mountain and valley. And valley and the mountain. So on the left-hand side is the P-type semiconductor. Abundant hole are present. A lot of hole on the left-hand side, but a lot of hole live in the valley. So when you look toward the right, they see a mountain. They see an energy barrier. They got blocked by the energy barrier. So this is the energy barrier against the hole. And what's the height of the energy barrier? The built-in potential VBI times the fundamental electron charge. But for the electron, we know a lot of electrons on the right-hand side. But those electrons, abundant electrons, reside in a valley. When they look on the left-hand side, they see a barrier. They see an energy barrier that got blocked. And this is the energy barrier against the electron force. So what's the thermal equilibrium condition in terms of the concept of energy barrier? We see a lot of hole on the left-hand side, abundant hole on the left-hand side because this is the P-type, majority P. For the N-type semiconductor, a lot of hole on the right-hand side. So both group, majority group, when they look into the center, the interface, they see the same potential barrier. That's the thermal equilibrium condition of a p-n junction in terms of the concept of energy barrier. That's the key takeaway of this lecture. It's very important when we move on to explain other stuff in the fundamental semiconductor physics. I hope you take this in. Very important. Thanks for watching.